All right, so the next thing we're going to look at is the cyclic quadrilateral, and this says an exterior angle. Okay. Now, a cyclic quadrilateral is a quadrilateral inscribed in a circle so that all four vertices are touching the circumference. So if you draw a four-sided figure shape inside of a circle so that all four vertices are touching the circumference, that type of quadrilateral is called a cyclic quadrilateral. Ladies, gentlemen, an exterior angle is formed when one side of a polygon is extended. So if you have a polygon and you extend one side, which means just simply draw it longer, the angle that is formed on the outside is called an exterior angle. Now, if you draw a circle so that and draw a four-sided shape in it, so that all the vertices are touching the circumference, that shape is called a cyclic quadrilateral. So that is what we just said in essence. You have a cyclic quadrilateral and the idea of an external or exterior angle. All right, this is circle theorem number 4. Circle theorem number 4 says opposite angles in a cyclic quadrilateral are supplementary. Opposite angles in a cyclic quadrilateral are supplementary. Now, the word supplementary means add up to 180 degrees. All that this is saying is that this angle and this angle, they add up to 180. So that is beta plus gamma add up to 180. This is alpha, and I think this is phi. They add up to what? 180. Opposite angles in a cyclic quadrilateral are supplementary, which means they add up to 180 degrees. Number 5, that's circle theorem number 4. Now, number 5 also deals with the cyclic quadrilateral. Number 5 says the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. The exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. So what are we saying, guys? Let us say we have a circle. Inside of it, we draw our quadrilateral. Now, all the sides, all the vertices are touching the circumference. So that is a cyclic quadrilateral. Let's just say that this is A, B, C, and D. If we extend, let us say the side at B, extend it, the angle that is formed on the outside is called the exterior angle. Let us say that this is alpha. If this is alpha, this is also equal to alpha. Now, the angle inside is called the opposite interior angle. So the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. The exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. So 4 says opposite angles of a cyclic quadrilateral are supplementary, meaning that they add up to 180 degrees. And 5 says the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. Ladies, gentlemen, let's talk about Let's talk about the tangent to a circle. Now this says the tangent to a circle is a straight line drawn external to the circle that touches the circle at a single point. The point where the tangent touches the circle is called the point of contact or the point of tangency. So in my diagram, PQR is the tangent. The point where the tangent touches the circle, which is Q, is called the point of contact or the point of tangency. Guys, circle theorem number 5 says the radius at the point of contact is at right angle to the tangent. The radius at the point of contact is at right angles to the tangent. So in my diagram, I have my tangent. Now, the point where the tangent touches the circle is the point of contact. Now, if this is, let us say, P, Q, R, Q is the point of contact, O is the center, OQ is a radius. Because any line drawn from the center of the circle to the circumference is the radius. Now, since Q is the point of contact, OQ is called the radius at the point of contact. Ladies, gentlemen, the radius at the point of contact is at right angles to the tangent. Circle theorem number 6. The radius at the point of contact is at right angles to the tangent. All right, number 7, before we look at another example. All right, in this diagram, circle theorem number 7 says the angle between the tangent and the chord at the point of contact is equal to the angle in the alternate segment. The angle between the tangent and chord at the point of contact is equal to the angle in the alternate segment. So let's see if we can decode all of that. Circle. This is my circle. Let us say that this is my center. Well, the center not important. All right, a straight line drawn that touches it. This is my tangent. All right, this is the point of contact. Now, this line here is a chord. That's a chord. So this is my QS. That's a chord. Now, this angle here is called the angle between the tangent and the chord. But remember, the chord divides the circle into segments. So let's call this theta. Theta there is the angle between the tangent and the chord at the point of contact Q. Theta is the angle between the tangent and the chord at the point of contact Q. Now, if I now form an angle at the circumference, all right, I'm going to form an angle at the circumference. Now, you see this angle here, whatever it is, it's equal to this angle. Now, this one here is called the angle between the tangent and the chord. This one here is called the angle in the alternate segment. Now, the angle between the tangent and the chord at the point of contact is equal to the angle in the alternate segment. QT is a chord. So this angle here, if I call it alpha, is the angle between the tangent and the chord. That alpha is equal to this alpha. and the alpha at S is the angle in the alternate segment. Ladies and gentlemen, the angle between the tangent and the chord at the point of contact is equal to the angle in the alternate segment.